a great pleasure to introduce and welcome Bill Freeman from MIT, who will talk about the LabelMe dataset.
Great, thanks. It's a real pleasure to be here. Thank you for asking me. So when I was a kid, you go to a movie theater, there'd always be a short before the movie. Like you see Bambi, and then you see the main thing, you know? And it was really fun. They don't really do that anymore. So I thought I would maybe bring that back and have a little short before the main talk. This is because I was preparing this talk, and I saw this. Oh, I'd love to show that to them. So I think I will. So this is a short before the main thing. This is creating and exploring a large photorealistic virtual space with Joseph Civic, who used to be a postdoc with me, and a grad student of mine, Biljana Kaneva, and Antonio Taraba, who's a faculty colleague, Shai Avidan, who works at Adobe, and me. So here's the idea. You want to start from a picture and just be able to drive, just go anywhere from that picture. And what we're going to do is use the world's other pictures to help us do that. So we want to make a little photorealistic virtual space. It doesn't really exist anywhere. But we're going to go look at the world's images and see, suppose you started there and you wanted to go left. What's a good picture to put there? And let's blend it in properly and seamlessly and just put it there. And then we can make a sort of large photorealistic virtual space. You can just start from a photo and just drive, go forward, backward, turn around, and explore this large virtual space. So first of all, why would you want to do this? Well, it might be a nice hook for photo sharing websites. You could start from your picture and drive off and see where it takes you. You know, go to somebody else's picture. And it might be useful for these large virtual worlds like Second Life. It's just a sort of infinitely large photorealistic virtual world. And maybe for computer games, maybe for movies and ads. So let's see. OK, so here's what we did. So I got to say, I got to lower expectations a little bit. The results are not going to be perfectly seamless. There are some, you can see artifacts. But here's the approach we took. We grabbed 6 million images off of Flickr. And if you just do them naively, it doesn't work at all. You just go off into crazy images. But so we grouped them thematically, and we wanted to stay within a theme. So we built a classifier to classify outdoor scenes, or to classify bar scenes, or to classify these different categories. And then once we were within the category, then it worked pretty well to let us drive around in this virtual world. So how are we going to match up images? There's, you know, you're not going to be able to find a picture which, starting here, would give you a photorealistic match to these things. So we're going to lighten up a little bit and let it have a match in terms of orientation structure. So we use this so-called gist representation. I'll talk about it in the second talk as well, where you basically break the image into blocks and look at oriented energy at different spatial scales and different orientations across each block, put that into a long vector, and that's your representation for the image. And that's what you're going to match on. And by the way, that's sort of a consistent theme in computer vision now. Everyone's discovered that matching image intensities, that's not good. Matching orientations, that's good. So there's a lot of nice flexibility that gives you. And as I mentioned, we picked these sort of semantically consistent themes, and we built a classifier to sort of pre-process these 6 million to pull out 100 or 200,000 within each scene. So we have a skyline theme, a landscape theme, a street theme. And if you stick within, if you only grab pictures within that theme, you can do pretty well. If you start mixing themes, then you kind of tend to go off into hyperspace. And then we have some basic motions that we allow our joystick operator to have. You can go forward, you can rotate, you can go left or right. And you know, you kind of do what to make this happen, you sort of do what you would expect. To move the camera, you go and look for pictures that match this one in that part of the frame of that picture. So let's see. There's camera. And again, we match not directly on pixel intensities, but on actually a combination of color intensities and this orientation structure. And then you have to play games to make it look good. You can't just plug it in. You have to wiggle it around to find the best fit. Then you have to use dynamic programming to pick the best cut. And then you have to use Poisson blending to put it all together to, again, to try to minimize the artifacts. I'm not quite clear what all your backgrounds are. Is Poisson blending a term that people know? Anyway, it's a really cute idea that the graphics folks have come up with, which is to say, if you want to paste two pictures together seamlessly, if you just overlap the pixel intensities, you're going to see the cut between them. You can't really hide that well. But if you just cut and paste the gradient values and then integrate everything up together, you don't include the gradients for that cut, and you do a great job of hiding the seam between images. So we use that approach. And then, okay, so rotation is just a slight twist on that. Instead of looking for a match there, you look for a match that fits a rotated image that would be there. And then zoom is kind of the obvious thing. You find an image which is going to match there. Do the same thing. So let me show you some still images first, and then I'll show you the video. So if you just start from this image and do the operations I described, you can make this little infinite panorama. And, well, just to point out the artifacts, this doesn't look like a good one to me, but the other ones look pretty reasonable. And here's behind the scenes. These are all the different pictures that were actually used to make this panorama. And then again, we had to use dynamic programming to find a seam that broke the fewest gradients as it went from top to bottom in the image. And then the same story with zooming in. So you can go on the street and just start driving forward. Just keep on driving. And it keeps on finding pictures which fits there, and here's the seams as they put them in. Okay, so here again, and still before I go to the video, here's some panoramas that we made from this little virtual world that doesn't exist anywhere, but maybe it'd be useful to have in your computer for Second Life or something. Okay, play the video. And as I said, there's some artifacts. I'm not really happy with it, but it's a fun start, and I think there's no reason you just can't do it better. So let's now you see the animated version of what I've been telling you about. We start from a street scene and just keep on driving forward, and it keeps on, finding images that fit in there and putting them in, and away you go. Now let's rotate. And you can tune this depending on, it all really depends on the set of images you're searching over to blend in. And then finally, let's just do translation again. So this one, these are all, I guess, in the city category. And skylines can just kind of keep on going forever. So you can also place the images, sort of make a little, explore this virtual world by putting the images all where they would be. Here's some more driving. This one, as the more I look at it, the more I'm bothered by the artifacts. But anyway. Okay, so let's explore famous sites. You can start from this picture and then just go off to the right. What's there off to the right from the Hollywood sign? And, well, a lot of interesting things. Oh yes, here's a. So we go from there. This, yeah. We end up at a famous site. And you might wonder, you know, what is off to the right from the XP screensaver? Okay, another thing you can do, you can make an image taxi. You say, well, here's where I'm starting from. Here's the image I'd like to get to. Could you drive me from here to there, please? And so it you know, again, does dynamic programming and finds the best set of forwards, rights, and pans to get you from one image to the other. And again, this type of thing might be useful for a photo sharing site. Okay, so that was the short before the main feature. Are there questions about that?
So are you manually you're manually selecting these directions, right? Because the system doesn't know where to go.
Right, right. But that's the manual. Oh, sorry. The question was, are you manually selecting these directions that you go in? And yes, but I mean, that's the part that you want to have be interactive, so you want to let the person do that. Except I should say for the image taxi, we weren't manually selecting it. That was, the user selected the start and the stop, and then the program found the taxi path that would take you from one to the other. Okay, you can go out and get popcorn. And here's the main feature. Let's see. So my lab does a number of things related to image search in collaboration with, and I work closely with Antonio Torralba, who used to be in my lab, but now he's a professor at MIT with his own lab. But he and Rob Ferguson and I worked on our collection of finding 80 million images and what can we do with them. But I understood that Rob talked about that when he came to Google recently. So I'm talking about a different but related sort of web search for images project that we call LabelMe, and then a use of LabelMe. So, and I should say, these two pieces are part of the thesis work of a student of mine who just graduated, Brian Russell, and then also the co-advisor and really a person who had a lot of intellectual input into it was Antonio Torralba. So I want to credit them. I'm behind both of them in the author list on this work. So, and what I want to do is talk about two pieces. One is LabelMe, which is this online set of labeled images. And then the second is an application of that labeled training set to use it for object recognition. So LabelMe is an online database of labeled images. So what's a labeled image? You get an image and you draw a segment around some object and you label the segment. And that's one polygon label for one image. Obviously, for object recognition, you'd like to have a big data set of those. And we wanted to let the world help us do that, so we made a web-based annotation tool, and anyone in the world can go and label images for us, and they do. And that's nice. You know, talk about coals to Newcastle. The purpose of this slide is to say the importance of having large data sets for machine learning. But I think you guys understand that, you people. So for language, you know, 1 million samples is good. For character recognition, data sets are on the order of, you know, 10,000 samples. For object recognition, the data sets are much smaller. We'd really like to make them much bigger. And you want what would the ideal computer vision labeled training set? It would have, you know, an infinite number of object classes, say 30,000. It would have many, many examples of those, and many objects per scene, and many examples of each object, and many different scene categories. So to try to strive toward these goals, we made this online tool. And we supply the images like these, and then the users go online and label rectangles, label polygons, and assign names to them. So here's a screenshot, and here's a sort of typical labeling for tree and a car and a wheel and windshield and so forth. And if you Google LabelMe, you'll find it. And I assume that you're very careful about Google becoming an English language word, so I should say if you Google brand search engine, the LabelMe, you will find it. So these statistics are old, but they're the right orders of magnitude. We have about 200,000 images available for labeling and about 200,000 object annotations. Obviously, many images have more than one annotation. And at least 41,000 images with at least one labeled object. And also we have sort of scene categories as well. So if you should go to the webpage and you can play with it. If you type in kitchen, it'll give you lots of examples of kitchen scenes and labeled versions of them. Or street, same thing. And here's some labelings of individual objects. Here's balcony, and then examples of the image crop that it came from and the silhouette showing what part of that image crop was labeled as balcony. Here's chair. Again, the image crop with the image of the chair and then the silhouette that the user defined as having this labeled chair. So here's a little all-at-once view of many of the different categories we have. This is a registered average of the images within each category. You can see we have orientation annotations on cars, different orientations, faces, and indexed by orientation of the face. So just some statistics. This is the number of instances that are labeled in the data set as a function of what, for the different rank, for the topmost and going down to the 1,000th most frequently labeled object category. So person is at the top, and then car, head, tree, window, and so forth. And you can see the distribution on this log scale of how many different object categories we have labeled. Yeah?
Each image is labeled by one person or by many persons?
It can be labeled. It's labeled, each image is labeled by more than one person. It can be labeled by more than one person. Typically, they don't label the same polygon. So when the image comes up, it's got the progress so far on it displayed. And then the new user can modify those edits or add more. And then just some statistics. So this tells what percentage of the image is labeled for the ones that are labeled. And most of the image have a small fraction of the image labeled, less than 10%, although some have every single pixel labeled. And the number of objects per image, most just have one object label per image, but it can go as high as higher than 15. And here's our progress as a function of time. We went online 3 years ago in the summer, and this is a snapshot from about, from a while ago. It's a bit beyond that now. I haven't updated this slide. And then here's our derivative, the number of new descriptions appearing as a function of time. So this is sort of as you'd expect it. The common words and common things were described first, and then now we only have occasional new categories coming online. And so that, there are a lot of issues, like what are you doing letting the whole public label your data set for you? Isn't it going to cause a lot of noise and problems? And so I just want to talk about that a little bit. So first let's talk about the quality of the labeling that we get from this totally volunteer set of people. And also I should say, just to sort of contrast it from like Louis van Aan's approaches, it's fun, but it's not like the most fun game you've ever done just to label these things. It's really, I don't know, I haven't really done much of it. I'm not sure what kind of person really enjoys doing it, but there are people who do it for us. So regarding the quality of the labeling, one kind of rough measure for what the quality of a labeling is how many line segments there are in the polygon that describe something. So in general, the more segments there are, the more care was taken to describe that outline. So we gathered statistics on how many segments were in each polygon. And then here's a pictorial representation. Here's the mean, and then the 25 percentile and 75 percentile polygon counts for these different categories. And so you can see, I mean, I don't know what your take-home message is when you look at this. When I look at this, I think, well, it's pretty good. On average, people are doing pretty reasonable silhouettes, and you can look at many of these and figure out what it is. For at least 25% of the time, people are really doing seriously careful labeling for us. And then even the bad ones, they could be useful. And then here's some of the extreme examples, the people who really took care. So this is, these are very elaborate. And then we also have extreme examples the other way, people who did not take so much care. And then we do get a certain amount of, let's just kick the tire on the system, see what happens. And testing and other testing and, just creative testing. But we can find these things and weed them out. So it doesn't take that much effort to just quickly verify what people have done. And we do that before we put it into the data set. Another concern is we made this choice to not provide a menu of object categories for people to choose, but rather to let them enter a text string for what the object is they labeled. And so you win and lose with that. We don't bias their descriptions towards some predetermined set of objects we think ought to be in these images. So that's good. On the other hand, you have a certain variability in the object category descriptions which you may not want. And so to address that, we use WordNet to help us determine what multiple labelings might actually be the same superior category for a given word. So is everyone familiar with WordNet? I'll take Sam to be the proxy for everyone because he nodded his head, so that's okay.
It's not a complete description of the ontology of English, but if you were an alien and you landed and you knew nothing about concepts, it would get you a long way.
Right. So you can, starting from a given noun, you can go up and down in the hierarchy of, like if you put in child, you can find out that it's an instance of a person, which is an instance of a living thing, and so forth, and go sort of up and down the tree. And so we can use this to take people's multiple different labelings and assign them to the same node in a tree. And we do that to help address the variability of people's labels. So using WordNet, then we can get a label that we come up with, like person, and find all these different labelings that people made that should be in the same category as person. And similarly with car, we can go and find out that taxi, in some sense, is an instance of a car and put it in the same category for car. Sorry.
If you're looking for girl, for instance, you still can't, or?
Yes, you still can, right.
Okay, it's just for some categories you merge.
Yes.
But for others, for most you also can't. Yeah.
Yes, we can search for both ways. We can search for the individual labels that people had, and then also we can search for these categories. So here's examples of the different categories using WordNet: tool, food, plant, animal, and then the retrievals that we can get within that category based on the individual labels of people. So under tool, we can pull out toolbox, knife, scissors, and corkscrew, and so forth. So this is helpful to address the many different words that some people put on their labelings. And then I have some slides, these are a little bit outdated, comparing our data set with others. It's really, certainly at the time these snapshots were made, you know, it sort of beats the others. This sort of collaborative effort by the web beats the individual databases that people have made. So in terms of number of categories, LabelMe is here, and number of objects per image. Number of categories is this axis, number of objects per image is this one, and we have this range, and others have a range with far fewer object categories. And again, this is because we took advantage of all the different categories that people labeled in our images. And then in terms of the number of labeled instances and the percentage of the image that they occupy, we're at this region of the scattergram. Let's see. And again, for a number of object categories and number of instances of each category, we're on this blue line, which is in the right direction relative to these other data sets. And similarly with number of control points. Yeah.
Do you mind an interruption there?
Please.
So I guess when you're drawing curves like this, one thing that is implicit is you're operating at some level of precision. So you're saying like, well, at 90 whatever % of the objects that are labeled X really being an instance of X, then the curve looks like this. And so one thing you could try and estimate is what does that curve look like for something like Flickr. So here's something you could do. You could say, pick a number K, and then use Flickr as a labeled data set in the following way. Type the name of an object just as a naked text query into Flickr, and take the K top hits.
Okay.
So by spot checking, you could try and estimate for various values of K what the precision is of that, and try and match that precision to these simple data sets. And then we could try and sort of say, well, where is Flickr as a curve on that? So of course, the problem is that these aren't really labels, but because a lot of people use them.
You mean Flickr for the tags, for example? Yeah.
It's not really
Right.
in the explicit sense.
Right.
But
So
because people use them,
right.
if you type the name of a thing, you do, at least the top few hits are generally, they tend to.
Right. I guess some sort of the way I would see what you're saying is that you know, all these data sets, pretty much if you put in the word for something, you're going to get a picture of that thing. And then whereas Flickr just creams us in terms of the size of its data set, but it's very inaccurate in terms of what the precision of what you'll pull out. Yeah. And so you want to take Flickr and put it on this chart somehow.
By restricting it to.
Yeah. Okay, that's a good thought. Let's see. Kevin Murphy keeps pointers to labeled image databases, and you might want to look at that if you're interested in using some of these. So that's kind of the data set itself. And then now let's go and do data mining on our data set. So one thing that's of interest is a lot of the segments that people label are overlapping. And well, what does that mean? Well, it could mean one thing is behind the other. It could mean one thing is a part of the other. And so you can use these overlap segments to pull out what are parts of other objects. And so we come up with an overlap index for what fraction of a polygon is completely within another polygon. And if you find many instances of one label always being inside of another label, you might decide, oh, that's a part of that other thing. So we can pull this out from the labelings that people have made for us and build object part hierarchies just from their labelings, even though we didn't explicitly ask them for these. So you might imagine what are going to be the parts of a car from the side, a car from the rear, or a sky. You didn't know a sky had parts, but it does. So car side has parts that we, in effect, discover from the labelings that people have done for us. Wheel, car door, car window, and tire. Okay. Car rear has taillight, wheel, license plate, car window, and mirror as its parts. And a sky has the sun, has the rainbow, has the moon, has clouds, has bird, as parts of the sky. So that kind of falls out of the labelings that people do. And so here's another display of that. Mountain and its parts, building and its parts, including air conditioner and a spider. Patio, awning, text, marquee, pillar, balcony. Person has kind of an obvious set of parts. Face, head, hand, hair, eye, mouth, nose, neck, and the sky I mentioned. Here are cars with their parts indicated, and people with their parts indicated. And you can also pull out depth ordering. Okay, so here's a little puzzle. Suppose you have two polygons and they intersect. How do you figure out which one's in front of the other one? Any ideas? Yeah. So you count the number of segments that each one has in the intersection when it's inside the other one. And you're exactly right. I didn't hear who said it, but thank you. Didn't see who said it. The one with the more polygons is the one that's in front. And so it's a heuristic that almost always works, and we can use that to again, even though people didn't explicitly do it, we can pull out a depth ordering from these labeled images. So here's an image that was labeled, and here's an ordering of the objects that were labeled in depth, and similarly for this. And it works pretty well. And let's see. So what was it? Okay, here's this one is a failure example of that heuristic, but in general it works. It's pretty reliable. Yes.
A question about that. Does that sort of assume something about the labelers in that if there's a big object, people just won't bother to label as much detail? So like you said that cathedral, like the person who went crazy labeling the cathedral, that had a lot of control points on it.
Right.
This kind of breakdown. Sort of, does this work because of human habits?
Well, actually, no. I mean, I think the sort of assumption underlying this is that the people put down polygons at a sort of fixed rate as a function of the variability of the boundary. And if you make that assumption, then this heuristic would hold. I mean, well, the answer is yes. People's habits do enter into this, and it's a little bit a product of the way the world works, and a little bit a product of the way humans work when they label the world. But I mean, I think you can make a mathematical assumption about how frequently they change straight lines as a function of the object boundary, and you would arrive at this heuristic for how you should label what's in front and what's in back.
Something, you're inclined to just, you're not going to draw details, right? That's pretty much it,
Well, people vary is what they do. I mean, you saw from those different 75 and 25% points on the number of polygons, people have a real a spectrum of the way they label. I mean, I think the bottom line is yes, people's habits are folded into this, but you can try to pull out things that statistically do the right thing. Then another thing you can pull out of this is where do objects appear in images? So now this, of course, relies on the fact that our images are taken by a photographer. We don't just toss a camera up in the air and click at a certain random instant. And because these were photographed by people who put the ground plane in a particular place usually and center things on the objects they're looking at, you get this fairly reliable distribution of positions of objects within the frame. And you can use that for identifying objects in some new image. These are priors on where things should appear. So that's the piece I wanted to say about this labeled data set. And of course, it's free for everyone. and you might enjoy labeling these. Try it out. Are there questions about it before I move to the last part? Okay. Yeah.
So when I look at the curves of the number of labeled images is a function of the number of classes, it looks like once you pass the 200 or 500 classes, you'll only have very few labeled images per class.
That's true.
And I imagine then there you can do very little analysis.
I think that's true. Yeah, I think that's true. So how might you use this labeled data set? Well, you could build an object detector that would take these, look at a local bounding box that bounds the label of something and build an appearance-based detector for those objects. That's a very natural thing to do. We've done that. A much more interesting thing to do is to exploit the regularity of scenes to help identify objects as well. And so what I'm going to do now is sort of tell you the sort of research theme of my colleague Antonio Torralba, who's really gotten the computer vision world psyched about this approach. And kind of here's from one point of view of describing it is that nature is kind to us. Nature is kind to us in many ways. At a pixel level, nature is kind to us. When you look at a pixel, it's not just a random collection of dots. It has a lot of structure, and images look very different from from just random Gaussian noise, and that's nice. And people have looked at that and used that for a long time. Another way that nature's been nice to us is in terms of the scene itself, the whole picture itself. If you look at a scene, it's not just a random collection of objects and pixel clumps in the world. It has a structure at the whole picture level itself as well. And that structure you could call context. And that, we as humans use it all the time in recognizing objects. And the field is now beginning to make use of that to recognize objects by computer as well. So, if you imagine walking down a sidewalk, you can sort of picture what objects you're going to see. And if you all wrote them down, I bet you would come up with a list that was very similar from one to the other, what you expect to see as you're walking down a sidewalk. So, so that kind of regularity can help us recognize objects because we know what is likely to be there. So again, we have those priors just from the LabelMe data set, and Antonio has done previous work at trying to estimate where objects are likely to be based on the entire picture. Here's another sort of a demonstration of the fact that you yourselves use context when you recognize objects. Okay, let's have a little poll, all right? What object is that? Okay, what object is that? Excellent. Now what is so cool about this, and this is just a very clever demo that Antonio made, those are the same pixel values. They're just rotated one from the other. And so what does that mean? So you weren't using your local feature detectors to figure out that that was a car or a person. You were looking at the whole picture, and you were saying, OK, building, road, something vertical there, probably a person, And then horizontal over there, well, it's probably a car. So you were using all this other information to do your object detection on this thing here, because the local evidence wouldn't give it to you. It's the same as the local evidence for that other object. And so that's kind of one of the new directions that computer vision is taking, sort of led by Antonio, is to take advantage of all this information here as we try to estimate what's there. And that's what we're going to do with this LabelMe data set. Here's another example. I don't know, have any of you seen this before? Okay, all right, maybe you have. So anyway, so here's our colleague, Rob Fergus. And you can all look at this and you make up a story about what's going on, even though the visual evidence is really rather impoverished, pretty low res. That's because you're so smart, but you're actually too smart because you got it wrong in this case. It's cleverly cooked up to not satisfy those regularities that you assume when you interpret objects. And so, this is, it's a different interpretation than what you were making. He programs trash, he's got these beer cans. But that just shows you how much you're taking advantage of those regularities, which usually are correct when you interpret the visual world. So that's what we want to do here for the last 10 minutes of this talk. Here's the, and again, I'm presenting this work, but I just got to give credit to Brian Russell and Antonio Taralba, because this is really their baby. You take an image. Sorry. You take an image, and you go into the LabelMe database and find the other times you saw something that looked kind of like that, like the whole image. So again, this is taking advantage of the world being nice to us, not just at a local patch level, but at the entire picture level. I think there's a similar scene in there somewhere, and I want to find examples of those similar scenes. And so you go pull them out and find them. Now we've got a labeled data set of similar scenes with objects labeled, their positions labeled, and they're all similar to this one. And so then we're going to use that to pull out what the objects in this scene are. So we're going to take advantage of, we also have a kind of bottom-up, patch-based detector in here as well, but we explicitly take advantage of this contextual information that the humans are so good at using. So just to kind of go through at the top level what the pieces are. So you might ask, how do you find similar scenes? Pixel values, they might not work. You might not find something with the same color blue and so forth. So again, we're going to go to this direction that people in computer vision have found so useful, which is to look at sort of orientation structure of the thing. And so we're going to take this and convert it into a 150-dimensional object that describes orientation as a function of position within this thing, and look for other images which have similar orientation, sort of texture-y structure. And now it turns out it doesn't always work. So instead of finding just the one, we're going to take these guys and cluster them, because we pull out not just the desired cluster, which matches this one, but we also pull out some outliers. So we're going to take our retrieval set and cluster them based on their labeling. Because now once we're in this world, we've got all this extra information. We've got the labels, polygons. So we're going to cluster them based on their labeling and their labeled values. And then with this set and this original image, we're going to find the cluster and the object values which best explain our input image. So this is a way to take advantage of, again, both local appearance-based matching and also this scene context. So let me just go through this in more detail. So again, to do the matching, we want to rely on this sort of squinty-eyed view of the world, this sort of texture as a function of position view, which is this gist. And so you measure the energy strength, the contrast strength at 8 different orientations and at 4 different spatial scales and at 16 different positions, and string it all into a big vector, and that's your low-D representation of this image. Now this kind of tries to find this sweet spot. It's high dimensional enough to explain a lot of different images and to be somewhat discriminative about one scene versus another, yet at the same time it's low dimensional enough that you can hope to find good matches in there and hope to generalize well. Whereas pixel intensities don't really satisfy that. So let's say this is our input image. Here's what we pull out. I don't know how well you can see these, but a lot of these are pretty good matches, just in terms of things with the same objects around there. These are street scenes, and okay, this one has a person, and this one, there's people there, but you can get a good clue as to what you should see in this image by looking at all its friends that were pulled out of the LabelMe data set. And again, all these ones now have labels on them. So it's going to help us to interpret that input image. Here's another example, sort of office scene. And here's what it pulls out. Now, it's not always right. Here's 2 plates on a kitchen table. But many of these are correct. And so you can ask the question, how well is this representation at telling you what the category of the picture is that you're looking at? And so people have done this. This is a little subfield in computer vision, not called object recognition, but called scene recognition. What's the general scene that you're looking at? So this one would be conference room scene. Out there would be, patio scene or something. So here's a list of 16 candidate scenes and percent correct. And here's different representations used in a sort of nearest neighbor matching, I think that was it, from a labeled training set. How well does the representation do at letting you find the correct category of a scene just by matching a labeled training set? And the gist does as well as any. So we'll use that. And then, as I mentioned, they're not all good. So here's another office scene. This is a student office scene. Your offices are cleaner than this, but anyway, here's what it pulls out. And well, you notice there's, so some of them are good. Let's see, these are the good ones circled. And then good means basically other examples of the same general scene. And then there's some bad ones. And bad means these just really don't have the same objects in them at all, even though their orientation structure is a function of position, happen to match pretty well the orientation structure is a function of position of the other one. Yes?
I'm wondering if you, sort of exploring this line of work, if you draw any distinction between scenes that are distinctive because they have global structure, like looking at a building, you have a lot of repeated structure, and you tend to have similar vanishing points and this sort of thing, and scenes that are characterized by a collection of objects. So like I look at this and I don't think of this as a scene the same way I think of a street, looking down a street as a scene.
Right. Well, that's yeah. I mean, that's kind of the part of this that I find cute, actually, is that there is all this additional regularity in the world that we don't really notice that lets you take advantage of the fact that in our database, for one reason or another, there are a lot of photos of things with these kind of same objects in the same kind of places. And I agree that there's going to be a lot more variability than you would expect from a European street scenes or things like that. But context is powerful, and we use it all the time. And I think, and that's what we're trying to tap into. And I think perhaps your point is that it's not going to be as reliable as context, say, on a building from one window to the next, and that's true.
Or maybe there's complementary approaches that some work better in some
Yeah.
circumstances for analyzing the entire scene than others.
Yeah, right. So the important thing is to know how well, to know what the variances are, to know how powerful your inference is or not. So this isn't the only thing we use here to identify the objects. We're also going to use a local appearance-based detector as well. Okay, so let me go through this quickly. The idea is in our retrieval set, we get some that are good, some that are not good. So to try to make this somewhat robust, let's cluster the ones that we have come back. And again, we're going to cluster based on the labels of the objects that come back and look for consistent sets of those. So we built a probabilistic graphical model to try to describe these relationships. There's a scene variable that influences what objects are labeled in the scene and what those positions of those labeled, of the bounding boxes of those objects are. And so given any retrieval set, we try to fit this model to it, and we have a prior on the number of different categories that we're going to come up with. And we use this to try to break our retrieval set into some small number of categories. Sort of a simpler way to do this, you could just take the labels of the retrieved objects and their bounding boxes and try to do k-means clustering on it, for example. But this is a somewhat more sophisticated approach to trying to get a similar end. And so let's look at the clustering we get then. Again, here's the full retrieval set for this image. And by doing inference in this graphical model based on the labels and the positions of the retrieval set labelings, we find that the things which have the same kind of squinty-eyed appearance as this one fall into 5 different clusters based on what their labelings are and what their positions of those label objects are. Here's cluster 1, which, again, it's clustered based on the similarity of the objects within this cluster. It has a lot of monitoring. This is the right cluster for this one. It has kind of monitors, office scene. Here's another cluster that came back that looked kind of like this one in terms of very, very loose visual appearance, but has a whole different set of objects. So this was assigned to a different cluster. This is kind of close-ups of people, and that was assigned to its own cluster, and similarly. So then, let's see, and so here's kind of what you pull back. You'll get a number of different clusters and how many times each cluster shows up in the retrieval set. You get those images, and each image has a set of objects and a set of probabilities for each one of those objects that it shows up in an image from that cluster. So if someone told you which cluster this image was really in, this would be your prior probability on what objects ought to be there. So now we have a much simpler problem of just finding which cluster is this. And then also tells you where those objects would be. So you've pulled out a whole lot from this, kind of from 2 things, from the fact we have a labeled data set, and then also from these sort of kind of regularities of the world, that we really do have a lot of pictures that are kind of the same kind of thing as that in our data set. And so they have similar objects and somewhat similar positions. And again, this is the same, trying to tap into the same thing that let you all decide that that blob at one orientation and one position was a car, and a different orientation and position was a person. This is the same stuff we're trying to take advantage of. So just another picture of the same thing with a different input image. Here's another image, and the different clusters that we put the retrieval set into for this one. So again, this, I think, would be the correct cluster, you would say, for this image. It has similar objects, similar positions. And here are some other clusters. This one image was assigned to its own cluster. Yeah?
How can you cope with the prior distribution of objects in your data? It's probably very skewed. Some objects are more often seen in the LabelMe dataset than others. In that case, when you are retrieving, it's also going to be, say, you're going to have more cars. So there's going to be a bigger cluster of cars, even if there was no car in your thing, just because there was more car in your data.
Let's see.
Or maybe I'm wrong. But
well, I think that...
If you're looking for an object that is rare.
Yeah.
So that's the...
Right. Well, so there's kind of 2 entities that we're talking about here. One is the kind of the scene, and one is the object within a scene. Either one of them being rare is going to hurt you, definitely. I think, I mean, after we talk about it later, I think the prior statistics are sort of taken care of naturally by this graphical model, but we can talk about that afterwards. So we, let's see, I did this. Okay, so, all right, so, and we also get the position. So here's the procedure. Get a new image in, and you want to label all the objects in it. You go find this gist representation, find a set of similar images to it from the data set, and then we cluster them, find their objects. Now we have a prior on where the objects are going to be for each of the different clusters and what the objects are. Now we have to go finally and integrate that with, we do indeed have a local appearance detector that we run on the image as well. So we have 2 sources of information as to what objects are going to be here. One is just kind of search around with a patch and find if it looks like a keyboard. And the other is ask what kind of scene we're in, and might that have a keyboard, and where would it be? And so we combine those 2 in a final graphical model here. And these are our observed variables. This is the objects in our, that were labeled by people in our retrieval set, their positions. And these are the sort of an SVM local appearance detector outputs. And then the hidden variables we're trying to explain are whether or not these objects are there and what kind of scene we're looking at. And we use Gibbs sampling to do inference based on the observations of the shaded variables. And let's see. Well, first of all, let me show you something cute, which is to say that we get more power from the context part of it than from the local appearance detector part of it. So you can plot, you can unplug each component separately and make a detector that only uses this local appearance measure for objects, again, based on training, based on our outlines for the objects. And then you can also unplug that and plug in this context part, which tells you what objects ought to be there, and compare the areas under the ROC for each of the different methods. And for most of the objects, you have a higher area under the ROC curve if you just use this kind of scene context than if you actually use the local detector. It doesn't say you should throw away the local detector, but it just says don't forget this other part. Yeah?
It seems like you have another piece of information in analogy to image-based rendering. You have actual masks from LabelMe.
Mm-hmm.
So you could sort of say like, oh, I think I'm in a scene class that often has keyboards and monitors and mice.
Uh-huh.
Let me go and actually grab entire masks and sort of see if there's some
Right.
warping or alignment or.
Pretty much that's what this does. So we take a bounding box and we go step by step through the whole image, and they must do different scales as well, and find a good match. So that's pretty similar to what you're describing.
But that's a feature-based classifier, as opposed to just a
just a raw pixel
approach.
Yeah, okay.
You just say, like,
You're right.
there's 2,000 labeled monitors,
Yeah.
and they all have the full contour, and I'm just going to do it. That's why I said in analogy to image-based rendering.
I see. And sort of also what you're saying is, in addition or instead of these features that you might have, which happen to be little just features on a local scale, why not just use pixel values as a feature as well? That's sort of what you, I mean, yeah. I mean, there are other things to fold in there. Then you're going to lose if your monitor has a different color than the other one on the training set. But yeah. Let me close up soon. So put it all together, do the inference. What do you get? Well, you get reasonable detection. So you find these bounding box locations. Here's the input images. And here are the detected objects and where they were expected to be. So let's see, how's it doing? It's doing, this is just the bounding box, so it's not got the, it's not a polygonal description, it's a bounding box of where this thing might be. In many cases, it gets it right. Here's a funny one. This is a signal, which I'm pretty sure this is the signal and that's the window. So it actually missed, but because it has this prior on where signals are in street scenes that look like this, you know, it knew there should be a signal there, a traffic light, and that's obviously coming from the sort of top-down context inference as opposed to the bottom-up inference. See, I think I have this one. I don't know if this is going to be too small to go through. This is from the NIPS paper itself, which was sort of nicer than the previous ones that are from the thesis. So let's see, top are the input images. And then B are the detections using, again, both this top-down, this bottom-up method. So building, cars, and so forth are labeled. If you unplug the context and just rely on our local detectors alone, this is the labeling you get for those images. And there are a lot of false detections, which the sort of context helps suppress. Then this is the same for another building. And then here's a whole row just of bloopers. So here's the sky. I think there's I'm sorry, I can't even read this here, but this is probably like keyboard or something. Anyway, you know, we get it wrong sometimes. But I think I want to stop. I guess say this is sort of a direction that the field is heading in, and really it's been pioneered by Antonio Torralba. My lab has done work often in collaboration with him. Alyosha Efros and Derek Hoyam at CMU have also embraced this approach and are using it, and it's a direction that people are going in. You can, just by the fact, there's this notion that the world's images are not that disparate a set and they're really all similar one to another, you can use for all sorts of things. So Alyosha Efros has used it to make a very cute image filler-inner. You say, I want to get rid of this building and put something there. go find me an image that looks kind of like that, and then put whatever belongs there in there. And again, it's relying on that same regularity of scene context, and it does a good job. So that's what I wanted to go through. First, this LabelMe dataset, which is a nice label training set you can use for a number of computer vision applications, and then one application that we put it to, which is to take advantage of regularities of the entire picture itself to help figure out what objects are there and where they should be. So thank you.
We're right at the end, but maybe if there's
Yeah.
one or two questions.
So you were having these sort of high frequency detectors which were scanning the images in one path. The other path was low frequency contextual matching.
Yeah, I wouldn't.
Sort of relying on just the pixel orientation for contextual matching, whereas you could use the special configurations of heat maps that come from the detectors as a way of getting context also.
It's not exactly the way I would characterize it. So we did have these two sources, two different streams. One was, you call it bottom up, just looking at local image appearance, and the features we used were these little small versions of this gist, so basically orientation within a little box. The other one I wouldn't call just low frequency. I would call it, I mean, it's from regularities in the labelings by people of images that look similar. Anyway, but I suppose you could call it low frequency. I don't quite think about it that way, but.
I call it either way. I'm just referring to the specific implementation of the thing where if you use orientations or rough image measures as a way of measuring context versus using something you already learned from labelings as a way of generating special configurations for context.
Right, so we use the latter that you described, because we take this retrieval set, which matches the appearance, and we cluster the labelings. And that gives us a prior on what objects to expect.
What if you got the retrieval set by using the special configuration of heat maps you get from the detectors? The retrieval step itself would use a different feature, which was already coming from the labeled sets.
Let's see, so, okay, so just take me through it. You have a retrieval set, and it's labeled, and we want to use it to inform our detectors about context. And what is your proposal for doing that?
So what I'm saying is, to get your candidate clusters,
Yeah.
using a low-level feature, a gist type feature. Instead of using that feature, what if you take two of those detectors,
Yeah.
ran them through, each one would give you some heat.
I see, okay.
And use the heat map related configurations as a way of getting context.
Right, but actually we use human labeling on clustering. The retrieval set is clustered based on similarities of the labeled objects in them. So in some sense we do that, but we're using a very sophisticated detector. We're using people, and their heat map is outlining the objects themselves, and that's what we use to cluster those retrieval set images.
That's after retrieval, not on the input image.
Right.
You miss what you miss in the retrieval set.
Yeah. If we pick a bad retrieval set, we're sunk. But once we've got it, then everything's labeled, and we use those labels.
Okay, let's thank our speaker again.